Hi everyone. Today we're going to learn about the derivatives of sine and cosine. Our learning goal is to define the derivative of functions of the form y equals the sine of a function of x and y equals the cosine of a function of x. So we're going to start off with a proof. In order to determine the derivative of y equals sine of x, we're going to examine the graphs of two functions. So I just used Desmos to show you the graphs of what y equals sine x over x looks like and y equals cos x minus 1 over x looks like. And they're going to come into play during our proof. Okay, so this first part is just a proof. Once we know what the derivative of sine is, then we can just use it. But we're going to prove it from first principles again. So using limits based on the graphs above, use first principles to derive the derivative of the function f at x equals sine x. So we know that, like from first principles, that f prime at x is going to be the limit as h approaches 0. Here's our first principles formula that we learned way back when we started calculus of f at x plus h minus f at x over h. And in our case, f at x is sine of x. So we've got f prime at x is equal to the limit as h approaches 0 of the sine of x plus h minus the sine of x. So f at x plus h and sine of x plus h. F at x is sine of x over h. Now, from advanced functions, you may not remember, but you did learn that the sine of a plus b is equal to the sine of a times the cosine of b plus the sine of b times the cosine of a. So we can use that sum of angles, the sine of the sum of angles formula to expand the sine of x plus h. So we're going to do that next. So f prime at x is going to be the limit as h approaches 0 of, so using that expansion, it's going to be sine x cos h plus sine h cos x minus sine x all over h. So again, if we look here, sine x plus h expands out to give us this part here. Sine x cos h plus sine h cos x, but we've still got the minus sine x here. Okay, so we're going to use some properties of limits in order to finish this proof off. Okay, so the first thing I want to notice is that this first term contains sine x and this last term. So if we've got three terms on top, sine x cos h is one of the terms, sine h cos x is another one, and sine x is the third one. So of the three terms on top, two of them contain sine of x. So I want to, doesn't matter what order, I put these three things in on top. So I want to move this one so it's beside here and then leave the plus sine h cos x at the end. And another thing I could do if I wanted to is I could split this up into the limit as h approaches 0 of the first plus the limit of h approaches 0 of the second minus the limit as h approaches 0 of this third. So each one's over h. So I'll do this in stages so you can see what rules I'm using. I might use a few more steps than you would use. So first of all, I'm going to put these beside each other. So you can see that I'm just rewriting the numerator. Now, I want you to think about if we had just like 3 plus 1 plus 7 all over 4, that would be the same as 3/4 plus 1/4 plus 7/4. Okay, like you can see here, that's going to be 11/4. but we could also break it up this way to where we would get all fourths, 11/4 that way as well. Okay, so that's just a math equality that we can use. So we can use that here. Okay, so what I'm going to do, and also using the properties of limits, I can divide this up and say the limit as h approaches 0 of sine x cos h minus sine x all over h. So I've taken care of that and that, plus the limit as h approaches 0 of sine h cos x all over h. And then within this first limit, I'm going to common factor the sine x out of the numerator. So sine x, if I divide this first scoop by sine x, I'm going to get cos h, and minus, if I divide sine x by sine x, I get 1 over h, plus the limit as h approaches 0 of sine h cos x over h. Now, because this is the limit as h approaches 0, sine x doesn't depend on what h is doing. It doesn't matter what h approaches, so it can hop in front of the limit. And then same thing over here, cos x is in terms of x, so it doesn't matter what h does either, so it can hop out in front of the limit. So we're going to rewrite that here. So f prime at x is equal to the sine of x times the limit as h approaches 0 of cos h minus 1 over h, plus, so the cos of x is going to come out in front because it doesn't depend on h, times the limit as h approaches 0 of sine h over h. So now we're at the stage where we want to know what these things are. What's the limit as h approaches 0 of cos h minus 1 over h? And what's the limit as h approaches 0 of sine h over h? And we're going to do that graphically. So we're going back to what we learned in the very first unit, how to tell a limit graphically. So we'll deal with the cos h minus 1 over h first. So that comes first. So sine x times whatever that limit turns out to be, and then plus cos x times whatever that limit turns out to be. So if this is the graph of y equals cos x minus 1 over x, we should be able to find then the limit as h approaches 0 of cos h minus 1 over h. Okay, so let's pretend then that this is the h axis, okay? So let's look at our picture here. So as h approaches 0, so here's h approaching 0 from the left, here's h approaching 0 from the right. What's my curve doing? In each case, my curve is also approaching 0. So the limit as h approaches 0 of cos h minus 1 over h is equal to 0, which means that this limit way down here, the limit as h approaches 0 of cos h minus 1 over h is 0. So sine of x times 0. Okay? And the second limit we wanted to look at is the limit as h approaches 0 of sine h over h. So this is the graph of y equals sine x over x. So we should be able to, from this graph, figure out the limit as h approaches 0 of sine h over h. So again, let's look at our graph here. So as h approaches 0 from the left and h approaches 0 from the right, in this case, our curve is approaching 1 in each case. So the limit as h approaches 0 of sine of h over h is equal to 1, which means that this limit way down here is equal to 1, and so I can put a 1 over here, which means that f prime at x, sine of x times 0 is just 0, so that term is 0, plus cos of x times 1 is just the cos of x. So that's pretty amazing. So that means that if f at x is the sine of x, then f prime at x is the cos of x. And if you apply the chain rule to that, if f at x is the sine of a function of x, then f prime at x is the cos of that function times the derivative of that function. So for instance, if you had y equals the sine of x squared, y prime, using the chain rule, would be the cos of x squared times 2x, which you would write as 2x times the cos of x squared. Okay, so one thing that's really important to, and what we're going to practice a lot here, but x squared is the subject, is what you're taking the cos of. 2x, you're multiplying by the cos of x squared. Okay, so usually you put it out in front, so it's 2x times the cosine of x squared. All right, so there's our proof from first principles, and it works out to be nice. So if f at x were cos of x, then f prime at x is negative sine of x. I could prove that to you using the exact same methodology, but the cos of a plus b is a different formula, and we could go through and using our graphs, these same two graphs, we could prove that the derivative of the cos of x is negative sine of x. Okay, but I'm not going to go through that proof. It's very similar. Okay, and applying the chain rule, if f at x is the cos of a function of x, then f prime at x is negative sine times that same function of x multiplied by the derivative of the function of x. So you can think of this as the outer derivative, chain rule, times the inner derivative. And same thing here. Make sure you can see this here. This is the outer derivative for the chain rule, and this is the derivative of what's inside, inner derivative. Okay, so this is kind of our last big topic that we're fitting in this year. So determine the derivative of each function. Y equals the cosine of 3x. So we know that the derivative of cos is negative sine, so y prime is going to be negative sine of 3x. And I'm going to use brackets there to show that 3x is the subject. That's what I'm taking the sine of. And then also multiplied by the derivative of 3x, which is 3. But when I write that out, I'm going to want to multiply the negative 1 that's out front of the sine with the 3. So it would be negative 3 sine of 3x. Often when there's just a monomial after the cos, they don't use brackets to show what the subject is, but if you want to include them, by all means. Okay, so y equals x times the sine of x. So now we have a product rule because we have one function of x, plain x, multiplied by another function of x, the sine of x. So I have to do my first second function derivative. So my first function is x and the derivative is 1. And my second function is the sine of x and the derivative is the cos of x. So y prime is going to be the derivative of the first times the second plus the first times the derivative of the second. And there's no common factors in our scoops here, so we're done. That's as much as you could simplify it as well. So f at x is a sine of x squared. I think we already talked about this one on the first page, but let's do it again. So f prime at x. So the derivative of sine is cos, so it's going to be the cos of x squared in this case, times the inner derivative, so the derivative of x squared, which is 2x. But the way you would want to write it is this 1 that's out front, monomial, times the 2x gives you the monomials out front, 2x, times the cos of x squared. That's how the answer would be written in the back of the textbook. So the big error that people make if they haven't practiced enough is they would write the cos of, they would multiply the 2x and the x squared and get the cos of 2x cubed, which is totally wrong. So don't do that. Okay? y equals sine squared x. So for this one, we have to remember, what does sine squared x actually mean? So instead of finding y prime right away, I'm going to rewrite this as the sine of x all squared, because that's what sine squared x means. Okay, sine of x times sine of x. So now it's a chain rule first. So y prime, bringing the exponent down, so it's going to be 2 times the sine of x to the power of 1. So I'm really going to exaggerate this here. And then times the inner derivative, so the derivative of sine of x, which is cosine of x. So it turns out then that y prime is going to be 2 times the sine of x times the cos of x. So again, I put these ones side by side so you can see that they're different, and you have to know that they're different. So where is the squared? Before the x, so this means sine of x times sine of x, or sine of x all squared. And here we're taking the sine of x squared. Y equals the cos of 1 plus x cubed. So y prime, so it's a cos, so the derivative of cos is negative sine of 1 plus x cubed. And then we multiply that by the derivative of 1 plus x cubed, which is 3x squared. And then we're going to multiply the 3x squared and the negative 1 and put it out front. So y prime is going to be negative 3x squared times the sine of 1 plus x cubed. So y equals e to the sine x plus cos x. So y prime, so first it's an e, so an e works as it's e to the whatever. So that's your outer derivative. And then times your inner derivative is going to be the derivative of the exponent, which is going to be, so the derivative of sine of x is negative cos of x plus, or sorry, the derivative of sine of x is just cos x. Derivative of sine of x is cos of x, and the derivative of cos of x is negative sine of x. And that's probably how you would write it. It's simplified factored form, so you wouldn't need to do anything more than that. All right, G, y equals 2 times the sine of 3x plus 4. So the 2 is just a constant out front. So y prime is going to be, so leave the 2, the derivative of the sine of 3x plus 4, so the derivative of sine is cos, so cos of 3x plus 4. And then we're going to multiply by the inner derivative of what's inside, which is the 3. And then the 3 and the 2 can be multiplied together. So you would get y prime is 6 times the cosine of 3x plus 4. So y equals cos cubed of 4x squared minus 7. So again, I would probably first write this, just rewrite y as the cos of 4x squared minus 7 all cubed. So it's a chain rule first. So that's just y rewritten. So now I'm going to find y prime. So first I'm going to do the chain rule. So the 3 comes down times the cos of 4x squared minus 7 squared. Now the inner derivative, the derivative of what's inside here, the derivative of cos is negative sine of 4x squared minus 7, but that's still multiplied by the derivative of what's inside the 4x squared minus 7, which is 8x. So then how would we simplify that? So here's a monomial, 3, and another one, 8x, and another one, negative 1 here. So if I multiply those together, I'm going to end up getting negative 24x. So that takes care of that, the negative sign and the 8x. Times the cos of 4x squared minus 7 all squared. So the nice way of writing that is to write cos squared of 4x squared minus 7 times the sine of 4x squared minus 7. So that would be as simplified as you could make that one. Okay, I is the ln of the cos of x. Y equals the ln of the cos of x. So it's a ln first. So y prime, so how does ln work? It's 1 over whatever you're taking the ln of. So 1 over the ln of the cos of x. And then times the derivative of cos of x, which is negative sine of x. So y prime turns out to be negative sine of x over cos of x. That's the answer, and I would totally accept that answer, but the back of the book might say y prime equals negative tan of x, and you may ask yourself, why is that? So you've got to remember an identity from advanced functions, and that is that tan of x is equal to sine of x over cos of x. So that identity is used to go from this step to that step. As I said, I would accept this, but I'm looking ahead to next year. If you had a multiple choice test, you got this, but it wasn't one of the answers this was, you would have to know that identity in order to find it out. Or if you were trying questions and the back of the textbook said that, you would have to realize that negative sine of x over cos of x is the same as negative tan of x. And another thing that's important for I is realizing that this is a ln question with like chain rule, but it's not a product rule question. For this to have been a product rule question, it would have had to be ln of x times cos of x. So that would have made it product rule, but here, one way to make sure is I only see the x in one spot, one place. So that means it's not a product rule or a quotient rule. The x is only in one spot, okay? So that's another thing that I remember from previous years people struggling with. So if you're struggling with that, like to me it looks like a ln times a cos. It's not. It's the ln of the cos of x, and the x is only in one spot, which tells you that it's not a product rule or a quotient rule question. So be careful about that too. Whereas in J, we have the cos of x divided by x. That is a quotient rule question. X is in the two spots here. So we're going to do our first, second function derivative. So our first is the cos of x, and our second is x. The derivative of the cos of x is negative sine of x, and the derivative of x is 1. So f prime at x is going to be the derivative of the first times the second. So I'd want my monomials multiplied together out front, so that's the negative sine times the x. So that's going to give me negative x sine of x minus the first times the derivative of the second, all over the second squared. And if you look at the two scoops up here, maybe I'll use a highlighter for them. The only thing they have in common is negative 1. This is how the back of the book would write the answer, but if you wanted to, you could factor out the negative 1, but that's all you would be able to factor out. And it's really not going to change your answer that much. Okay, so K, the sine of the cos of x. So here's another one where, is this a product rule or isn't it? So the x is only in one spot, so it's not. It's really a sine question, but you're taking the sine of the cos of x. So be careful when you're doing these ones. They're kind of like chain rule, but you have to be really careful. So you're starting off with, what's the derivative of sine? The derivative of sine is cos, the cos of whatever it is you're taking the sine of. So cos of x. And then using the chain rule times the derivative of what's inside. So the derivative of cos of x is negative sine of x. And then probably not too nice of a way to write that. You might want to write it as put the negative right out front, because there's like a 1 in front of here times negative 1. So negative cos of the cos of x times the sine of x. So it's really 2 our answer is two things multiplying together. Negative cos of the cos of x times the sine of x. For L, we've got g at x is the ln of the sine of e to the x. So again, the x is only in one spot, so we'll start at the outside first. So first of all, it's a ln. So we know to find the derivative of a ln, it's 1 over what you're taking the ln of. So 1 over the sine of e to the x. And then times the derivative of the sine of e to the x, which is going to be the cos of e to the x, times the derivative of e to the x using the chain rule, which is e to the x. So your numerator is going to be e to the x cos e to the x, and your denominator is going to be sine of e to the x, again, which would be fine for me, but you might find the back of the book writing it as e to the x cotan e to the x, and that's because the cotan of x is equal to the cos of x over the sine of x. But this is fine. So again, this was a chain rule, kind of like with 3 links in the chain. So first it was a ln 1 over the sine of e to the x. Then to get the derivative of sine of e to the x, that involves a chain rule. So derivative of sine of e to the x is the cos of e to the x. But then you need to multiply that by the derivative of what you're taking the cos of, which is e to the x. And the derivative of e to the x is e to the x. So it's chain rule with 3 links in the chain. Okay, m, h at x equals the cos of x times the ln of x. So we have the x in 2 places here. The cos of x times the ln of x is going to be a product rule. So our first function is the cos of x, and our second is the ln of x. Derivative of cos is the negative sine of x, and the derivative of ln of x is 1 over x. So h prime at x, derivative of the first times the second, so negative sine of x times the ln of x, plus, with product rule, plus cos of x times 1 over x, which would be cos of x over x. And the scoops don't have anything in common, so we can't put it in factored form. So that would be our answer. The next one, we see the x in the numerator and in the denominator, so we have a quotient rule. So our first function is the sine of x, and our second function is 1 plus the cos of x. And the derivative of sine of x is cos of x. And the derivative of 1 is 0. The derivative of cos of x is negative sine of x. So using the quotient rule here, derivative of the first times the second, so that's going to be cos of x times 1 plus cos of x, minus sine of x times negative sine of x. So that's going to be minus negative sine squared x, which will make it plus sine squared x, over 1 plus cos x, so the second all squared. Now you might think our scoops don't have anything in common, so we're done, and then you look in the back of the book and say, wait a second, they've simplified it differently than me. Well, again, they've used an identity. A clue maybe for you is that you see a sine squared x here. So if you were to expand and simplify in the numerator, you're going to get cos of x plus cos of x times cos of x, which is cos squared x, plus sine squared x, and the most famous identity we know is that cos squared x plus sine squared x is 1. This derivative actually works out to be really cool. So the numerator ends up to be cos x plus 1, because cos squared x plus sine squared x is 1 by the most famous Pythagorean identity. And in the bottom you have 1 plus cos x squared, which means 1 plus cos x times 1 plus cos x. So this one in the top goes with one of the ones in the bottom, leaving you with the derivative to be 1 over 1 plus cos x. So you can imagine if you got this first answer here and you thought you were done and you actually found this is the answer, you'd be, how do I get from there to there? So again, this clue of seeing the sine squared x on its own, you're hoping there's going to be a cos squared x that you can pair with it, because cos squared x plus sine squared x adds up to 1. So that's a interesting one, which actually works out to a really pretty answer. So for O, y equals cos squared of ln of x. Again, the x is only in one spot, so it's going to be a chain rule question. You might want to rewrite it first as cos of the ln of x all squared. So all I did was rewrite y. Now I'm going to find y prime using the chain rule. So 2, bring down the exponent, times the cos of the ln of x, exaggerate there, to the 1. So that's the first link in the chain. Now we want to multiply that by the derivative of what's inside. So the derivative of the cos of ln of x. So first I'm doing derivative of cos, which is going to be the negative sine of the ln of x. But then my next link in the chain is I have to take the derivative of the ln of x, which is 1 over x. And then I want to write that in some kind of prettier way if I can, where I have a numerator and a denominator that makes sense. So I've got the monomial terms, the 2, the negative, and the 1 over x. So that's going to give me negative 2 over x. So negative 2, and there's going to be an x in the denominator, negative 2 over x. And then times the cos of the ln of x times the sine of the ln of x. And that's how it would be written in the back of the book. And p, y equals the sine of 3 to the x. So y prime, first it's a sine, so the derivative of a sine is cos of 3 to the x. But then we want to multiply by the derivative of 3 to the x. That's the inner derivative. And we learned the other day that the derivative of 3 to the x is going to be 3 to the x times the ln of the base, which is 3. So, and it would probably be written with the 3 to the x first, then the number ln 3, then cos of 3 to the x. So that's 3 things multiplying together, they can't be combined any further. And that would be your answer. Okay, so application a little bit, our easiest one, slope of the tangent. So determine the slope of the tangent to the curve y equals x times the cos of 2x at the point where x equals pi over 2. So start off, we've got y equals x times the cos of 2x. So it's going to be a product rule. So our first function is x. Our second is the cos of 2x. Derivative of x is 1. The derivative of the cos of 2x is going to be negative sine of 2x times 2, which I could write as negative 2 sine of 2x. So I could combine this monomial negative 1 and this monomial 2. Multiply them together. So y prime, so this is product rule, derivative of the first times the second, plus the first times the derivative of the second. So I can multiply the negative 2 and the x to get negative 2x sine of 2x. And we want the slope of the tangent at pi over 2, so we want y prime at pi over 2. So that's going to be the cos of 2 times pi over 2 minus 2 times pi over 2 sine of 2 times pi over 2. So y prime, or the slope of the tangent at pi over 2. So 2 times pi over 2 just gives you pi, so the cos of pi minus pi times the sine of pi. So if you don't remember them from your unit circle, you can make sure your calculator is in radians and type in the cosine of pi. So if I was going to do that, I would have to make sure I was in radians. Right now I'm in degrees, so I'd have to put it into radians. And then I can do cosine of pi, and it gives me -1 minus pi times, then I could try the sine of pi if I didn't remember it, and it gives me 0. So y prime at pi over 2 is -1 minus 0, which is just -1. So therefore m tangent is -1. Okay, so make sure you put your calculator in radians if you don't have the unit circle in, the sines and coses and radians all memorized. Okay, and our last question. Show that the derivative of y equals tan x is y prime equals sec squared x by using the identity that tan x is sine over cos x. So we're going to start off with y equals tan x, but we're going to rewrite it as y equals sine x over cos x, because we know the derivative of sine x and cos x. So we can think of this as a quotient rule then. So our first function is sine x, and our second is cos x. The derivative of sine is cos x, and the derivative of cos is negative sine x. And it's the quotient rule, so the y prime is going to be derivative of the first times the second. So that's cos x times cos x, which we can write as cos squared x, minus the first times the derivative of the second. So that's going to be sine x times negative sine x, which is negative sine squared x. But if you're subtracting a negative, you'd be adding all over the second, which is cos x squared. And then our most famous Pythagorean identity is that cos squared x plus sine squared x is 1. So the numerator is 1. The denominator I can write as cos squared x. And then knowing a reciprocal identity is that secant of x is equal to 1 over the cos of x, which means that secant squared of x would be 1 over cos squared of x. So just squaring both sides. So then it follows that y prime is sec squared x, which is what we were trying to prove. So that means, like if you were given y equals the tan of 4x, say, and you wanted to find y prime would be, so the derivative of tan is sec squared, so the sec squared of 4x, and then times the inner derivative of 4x, which is 4, so y prime would be 4 sec squared of 4x. Okay, I'm not going to ask you to do that, but just for next year for sure, for some of you that are taking first year calculus, important thing to know. All right, so I can find the derivative of functions that involve sine and cosine. So that brings us to the end of knowing the derivatives of all the special functions that you were supposed to know in high school. So please try the practice.